Now, there is another alternative, which is to use a formal relationship between the density matrix and the Hamiltonian. Basically, the density matrix can be seen as the application of the Fermi-Dirac function on the Hamiltonian. And the trick here is to choose an appropriate form for the Fermi-Dirac function that can be used in linear algebra. One of the first ideas was the Fermi operator expansion, which is to turn this into a polynomial series. And then all you need to do is to perform multiplications to get the density matrix. Since the matrices involved are sparse, this is a procedure that is linear scaling. This has been implemented in the chess library, which was originally part of BigDFT, but has been made into a standalone library and also ported to SIESTA by Stefan Mohr from the Barcelona Supercomputer Center. So this is another linear scaling addition to the SIESTA repertoire. It's not very much used still because we are working towards enhancing even more its performance by exploring on-the-fly construction of the basis set. Because the number of terms in this expansion depends ultimately on the number of basis set that you're using through the size of the spectrum that you are solving for. This is a technical point, but this is an important step in the solver portfolio in SIESTA. Another example of the Fermi operator expansion is this PEXI algorithm, which is a pole expansion plus selected inversion. The pole expansion looks like this. Now, this looks much more complicated, and it looks like a step backwards because performing an inversion of a matrix appears to be scaling quite badly, again, like cubic scaling. But in fact, we don't need all the elements of these inverse matrices. We just need a few because of the sparsity of the density matrix. So using a very smart selected inversion algorithm, we can get a workable approach, which in fact has reduced complexity, good size scalability. For quasi one-dimensional systems, it can be linear scaling, and even for three-dimensional systems, at most, it scales quadratically with system size. Here we can see a comparison. This is would be the cost of a diagonalization for a given problem, and this would be the cost as a function of the size of the system for this lower dimensional system.